do this. Welcome to Energy, Power and Propulsion, AESP 314. And my name is Mustafa Mugli. I'm going to be your teacher for this class. We are going to talk about the class structure a little bit today. We will have a little bit of introduction. We will go over the syllabus, talk about my expectation from you guys, and also your expectation from me as your teacher. We'll talk about course topics, and then we'll move on to a little bit of thermodynamics review if we had the time. Okay. Who am I? I got my bachelor's. A couple of you already know me, but for the rest of you who don't know me, I got my bachelor's from University of Tehran. It is located in Iran. 2012. My master's from UofSC in mechanical engineering. I have my PhD at 2018 in mechanical engineering as well, and I've been teaching for the aerospace program since 2018. Okay. Let's go over the syllabus. Let's start the syllabus. I have printed the syllabus for everyone. If you don't have the syllabus, I'm going to put it here. Yes, there is one student who has done the class. Let me know if you have any questions about the syllabus or anything as we move forward. Our classes is going to be on, of course you are already here, so you already know when the class time is, but it's going to be Mondays, Wednesdays from 2:20 to 3:35. And the office hours are going to be Mondays from 12 p.m. to 2 p.m. You can come by my office if you have any questions. I'm usually in the office during that time, but it is a good idea to send an email to make sure I'm going to be in the office if you have a question. Outside of these times, if you want to talk to me, send an email, we set an appointment, and we'll try to answer your I'll try to answer your concerns. We don't have any TAs for this class. It's just going to be me because we don't have that many students in the class. Usually, to be able to get a grader for the class, you need to have at least 30 students in the classroom registered for the class, and we only have 14 at this point. Take a syllabus just behind you. And please wear your mask. Take a syllabus right in front of you. Okay. We have two textbooks for this course. One of them is the main textbook, Aircraft Propulsion by Dr. Faruqi. And the other one is the Fundamental Engineering Thermodynamics. The second half of the book by Shapiro, Moore and Shapiro. We have a couple of optional textbooks as well. I will take pieces from these books. You don't really need to purchase them. I'm pretty sure you can actually find them because these are pretty old books. Some of them, not all of them. Any questions so far? So, let's move on to the topics of the course. The first thing we are going to talk about, which is this part of the class is shared with applied thermo in ME, mechanical engineering, is thermodynamic cycles. We will go over the thermodynamic cycles, Brighton cycles, Rankine cycles, whatever you need. And we will mostly focus on Brighton cycles because this is what we are going to use for the propulsion part of the class, essentially. And we will talk a little bit about dynamics and thermodynamics of perfect gases, a little bit of introduction to jet propulsion, one-dimensional flow, thrusters and efficiencies, and then we'll jump into supersonic flows and their properties, compressible flows specifically, and then we will become familiar with turbojets, turbofans, turboprops, all of those things. I'm thinking of covering a little bit of combustion because an aerospace engineer needs to have at least some familiarity with combustion that is going to happen in the combustor of the jet engine. and then we will have one chapter on rocket propulsion, especially rocket science. We have the lecture schedule. This lecture schedule we may not be able to follow completely, but this is my plan. This is my essentially wish list for the lecture schedule. This is what I want to do, but we usually need to change this a little bit based on the circumstances. And you are going to have 3 exams. We will talk about the exams later. Any questions so far? And okay, so this is hey. We don't have any. Let's see. Are there no extra syllabi left?
I got one.
You already have one? Okay. Let's talk about how the class is going to be conducted. I will record, I will prepare presentations for each class, but I usually don't use the presentation to teach. I usually use this Microsoft OneNote, or I mean in general, not during COVID time, during regular live, I use the board. But I will upload the presentations for you guys. So if you wanted to, I will try to upload them before the class. So if you wanted to print them out and bring them to class, you are welcome to do so. But I will also, since we are in still in the COVID times, I am recording this class as well as all of the classes, and they are going to be posted online. There is a YouTube channel. We actually, for those of you who have classes with me, we actually use that YouTube channel. I'm gonna post this on that YouTube channel. You can go and watch the other classes that we have had as well. Any questions about the class? If you were to miss a class for whatever reason, like you have to quarantine, you wanted to go on a trip or whatever, doesn't matter what the reason is, you have to watch the lecture that is posted online. Your attendance is mandatory, and by that I mean as long as you watch the lecture, as long as I know you have watched the lecture, as long as you have an idea of what's going on in the class, you should be fine. So you don't have to be present in the class, but you have to watch the lecture. And I check that attendance by giving you random quizzes. So in the middle of the class, I give out a quiz. I ask the students to solve that quiz. And if you were not in the class, that's not a problem. You can watch the lecture later and submit your answers through email, right? So, but you have to watch the lecture, right? And you only have a week after. It has to be done in the same week. Does this make sense? So there is no roll call in class, but you have to answer the quiz. I mean, there will be like somewhere between 5 to 10 quizzes overall. Maybe even more, I don't know. I mean, it really depends on the situation. And well, let's move on to the grading policy. So there are 3 exams. If you go to the page 4, there are going to be 3 exams, 2 of which will be counted towards your final grade. So essentially, if you do well on the first 2 exams, you don't need to take the third one. Or if you don't want to take the first exam, you can take the other 2. That doesn't really matter. If you want to improve your grade, you can take all 3, and you will use the 2 highest grade for your final grade. Those two exams are going to be 40%. These are midterm exams. 40% of your grade. Then we have 6 homeworks. Each homework is 4% of the grade, for a total of 24%. Then we are going to have a final exam, which is going to be a comprehensive exam. So everything we teach is going to be included in that exam, and that will count for 30% of your grade. And then we have 6% for attendance. Any questions?
So the quizzes that you give in class are just for exam purposes, basically?
Yes, they won't be graded. In addition to all of, yes, go ahead.
Is the final exam December 6th? Is the final exam December 6th?
Yes, it should be, I think so. Let me go back. It is on the schedule. December 6th, Monday, that's I think it's the first day of final exams at 12:30 p.m. And this is based on university schedule. I haven't chosen this time myself. For this classes at this time, the final exam is scheduled to be that day. Any other questions? I usually give out bonus points as well during the class. I may ask a question during the class, and whoever answers that question will get a bonus point. And each bonus point will be half a percentage of your final grade. So they can be worth a lot. And you can earn up to 20%, 20 bonus points essentially. So 20% of your grade can come from bonus points. For the quizzes, if you answer those quizzes correctly, you will usually get a bonus. Depending on the quiz, how hard it is, you will usually get a bonus point. Okay. So there will be some reward for answering the quiz problems. Any other questions? Oh, you have a question?
No, there's a question.
Okay. Yeah. And what else? Okay. So let's move on. Talking about and your grading criteria. If you want to earn an A, your grade has to be higher than 90, 85 to 89.99, B plus, and so on and so forth. I'll just come back to this. Some parts of the syllabus I may change as we go on, depending on how the class is going, but we will decide on this together, right? And you will be definitely, it will be announced many times. My expectations for you is to show up to class or watch the lectures online. Submit your work in a timely manner before the deadlines, unless you have already talked to me. So if you can't submit a homework, just send an email to me. I can't submit it at this time before the deadline. After the deadline, I don't even accept anything. Your grade will be 0, right? If you can't submit by the deadline, you already know 1 day in advance, right? Just send an email to me, ask for an extension. We will work on it. But if after the deadline you send an email to me, that's not acceptable. Ask your question in class. I really want all of you to be engaged in class. Engagement by you is very important, because there are a lot of things in your background that I don't know you have not learned, but I just assume you have. So I just may say this is something you should have learned like 2 years ago and move on, but you don't know any of it. So that will cause a problem. So engagement is important. If you have a question, make sure to ask. And there is no dumb question. Come to class prepared. By that I mean make sure you already know what we have already, you know what we have already covered in the class. You understand them. If you have a question, come to the office hours, talk to me, talk to your friends, whoever, doesn't really matter. Sometimes I ask questions, just random questions during the lecture. If you don't want to be asked any questions, send an email to me, tell me that I get anxious or whatever, and I will make sure not to ask you any questions. Any concerns, any questions? Anything? Okay. And I also want to know who you are. So we are going to go one by one, and I will ask you to introduce yourself. And as I said, I know a couple of you already, and I mean there are at least four of you in the class who are going to have one other class with me as well. I mean, even more than that. There are a couple of people who have the lab 1, 2, right? But we haven't had a class. But yeah, please go ahead and introduce yourself and tell me what your major is. What year are you? I assume all of you are aerospace engineering students. If not, if you're from mechanical or chemical, please say so. I also need to talk to you after the class if you're a mechanical or chemical engineering or electrical engineering student. What are your expectations from me, and what do you want to learn out of this course? Let's go from here.
Good. So my name's Cameron Brown. I'm aerospace. I'm a senior. My expectations for me, I feel like I'm an easy, as long as you're not like a horrible professor. I don't know, you know what I'm saying? I don't know what to say to that.
That's all right. You don't have to.
Okay, yeah, because I don't know. I've had bad professors, but I usually can't tell that on the first day. So, what I want to learn out of this course, I don't know. I mean, it is the first day, so I'm kind of open to, I guess, yeah, I don't know.
Okay. Thank you. Let's go with you.
I'm Jack Hill. I'm a junior in aerospace. As far as expectations, I'm not really sure.
You can talk about your interests or football or whatever. Whatever you want to talk about. That doesn't matter. It doesn't have. You don't have to go point by point.
All right. I guess I'd like to learn like stuff related to jet engines, things like that.
Okay. That's good.
Hi, I'm Igor. I'm an aerospace engineering major. I'm a senior. My expectations, learn a lot of stuff about propulsion, have fun. And I want to learn compressible fluid flow, so you can learn twice. Exciting.
Yeah. Okay.
My name's Drew. I'm in aerospace engineering. I'm in my junior year. I guess my expectations for you is get to know you well, because I'm also in your lab class later today.
Okay.
And what I want to get out of this class, I want to learn to kind of expand upon thermodynamics and put some use to it.
Okay.
Hey, my name is Karam. I'm a junior. I transferred here from Google Tech. I'm an aerospace major as well. I don't know what to expect from you, but I personally like the things that fly. That's why I got interested in aerospace. I want to learn more about like engines and flight aerodynamics, so maybe I can hopefully design an aerospace craft.
Okay. Okay.
I'm Emery. I'm a senior aerospace. My expectations for this class, I don't know, hopefully I can get some practical use for a lot of the math stuff.
Practical use for a lot of math stuff.
Like actually related to aerospace stuff, math theory and stuff like that.
Yeah. I understand.
Hi, my name is Trey. I'm also an aerospace engineering senior. My expectations, I'd like to learn a little bit about rocket engines and stuff like that. I like rockets.
Who doesn't, huh?
That's true.
Yeah. Sure. Go ahead.
My name's Camden. I'm a junior in aerospace engineering. I actually just switched to it, so I guess kind of what I'm hoping to get into on this class is kind of getting a good introduction, like nice, like aerospace specific class, and kind of really start digging into it.
Have you had aerodynamics?
Yes.
Okay.
Steven, junior aerospace. I know fourth or stuff.
This is my first time meeting you in person, right?
Yes.
Okay.
One of the 3 people who watched the
Good to see you.
My name is Lawson. I'm an aerospace engineering freshman.
You said freshman?
Yeah.
Okay.
Brand new. I'm really excited. Can't wait to learn how to suck, squeeze, bang, blow. I'm not good at chemistry, so the chemical parts scare me a little bit. Got C's in those classes.
Yeah, me too.
Yeah, this one. Another one.
Okay.
Name's Thomas.
I love your mask.
Thank you.
Yeah.
Name's Thomas Murphy. I go by
What was your name again? I
Thomas Murphy.
Thomas.
I go by Patrick, so it's my middle name.
You go by Patrick?
I'm sorry?
You go by Patrick?
Patrick, yeah.
Okay.
Aerospace junior. I'm excited to learn about like explosive combustion because I want to go into like military defense and work with firearms and stuff like that.
Yeah, explosive I mean, that's a little too specific for this course.
Well,
Fine.
I guess just like learning about rockets and stuff like that.
Yeah. But if you want to do some research on this, on combustion in general, you can talk to Dr. Vaughn, Sang-Hee Vaughn.
Okay.
Yeah.
My name's Zach. I'm an aerospace major too. I'm a junior. I was interested in rockets, propulsion, all that kind of stuff. If I want to learn about it, maybe I can take us to Mars. Figure out a lot of stuff.
Yeah. Okay. Nice.
I'm Nick. I'm a sixth year, seventh year, this year. I'd like to pass the class and learn about liquid propellant rockets.
Okay. He has never failed the class, by the way. Just kidding. Just.
I'm Joseph. I'm a junior. I'm also aerospace engineering.
Okay.
I'm just hoping to get a little bit more understanding of engine design out of this class.
Okay. Okay. Sounds good. So, how many juniors do we have? Just show of hands. Okay, we have a lot of juniors. But I mean, you're a senior. You have never been in any of my classes, orbital mechanics, or even lab 1, right?
No, I took a weird way through my I switched. I was biomedical and then mechanical and then aerospace. So
Okay.
I was doing it a very weird.
So you are in your 4th year, but you are not really a senior.
Yeah, no, there's no way to get out here and disagree.
Okay. Okay. For those of you who are junior students, which this is it essentially means that you haven't passed your aerodynamics yet, right?
Yeah.
No, the junior ones. Okay. Okay. That's all right. We actually had one student who was a junior student and took the class last year. Yeah, I'm talking about Nick. You ended up dropping the class, right? You want to share your experience with the students?
I came to the first lecture. There wasn't no syllabus things. He just kind of jumped into it. I was like, oh man.
I always do the syllabus. I never.
Maybe it's just blurred out in my head. It's terrible.
Okay.
I'm too.
Yeah. Yeah. So be careful, I guess. But this. Okay. But yeah. I guess that's it, right? Yeah, if this is your first class with me, you are going to have at least 3 more classes with me as well. All of the lab courses and also the orbital mechanics, flight and orbital mechanics, which is, in my opinion, that one is a harder course. Yes.
Did you not teach flight dynamics?
No, I never taught flight dynamics.
Really?
Yeah, that's Dr. Wang, Yi Wang.
I don't know why I thought you taught it.
I mean, we didn't have any teacher, so I should have, but I said no. Yes.
Are you guys changing how you're teaching the flight model, or is it the same way as the flight semester? As far as like splitting it into flight.
It is the same way, yeah. You didn't like it?
I
No?
would have preferred to go more in depth each semester, of like a flight semester than an orbital semester.
Yeah, that's probably a good comment you can give to Dr. Wang, who's, I definitely agree with you. A separate orbital mechanics course is definitely a better idea, yeah. Okay. So I guess we have to jump into if there is nothing else you want to know.
So like we're all aerospace majors, but this school is like 2nd or 3rd year is teaching aerospace, and we haven't had any graduates.
We have had a couple of graduates last year.
But we don't have any. Where are they? You know, I'm kind of concerned about not having the.
Is the program accredited yet or not?
Not yet. No, we haven't applied it. Was that your question?
Yeah.
We are going to apply for. I mean, you have to wait for the first graduates to apply. So we are going to apply this January. I'm actually very involved with the accreditation. What?
People who graduated, they easily transfer to AE.
Can you repeat what you said?
I thought the people that we had graduate, didn't they start as mechanical?
Yeah, because we didn't have the program back
Yeah,
then.
I
They had
thought
to.
the current seniors, I thought we were the first ones to start.
They transferred in their first semester, so most of them did. Well, as far as where they are, there were like 5 students in the first group, the pilot group. I mean, the second group, the seniors, are like Igor, Emery, Trey, Nick, Steven, and Lawson. I always forget his name. These are the second. I'm sorry. these are the second pilot group of the program. So we only have had 5 people in the first pilot group. 2 of them didn't graduate, or 6 people. 2 of them didn't graduate. And 2 other who graduated found a job. They were looking for a job. They found it. One of them is still in South Carolina, working for a CFD company, huh? Power tool company. Who are you talking about? Ryan is. I don't know the name of the company, but he told me he's doing ANSYS analysis.
Yeah, it's for power tool.
Yeah. Okay, that's good. Which makes me very happy because I was the one who introduced him to CFD. So. Yeah. And yeah, everyone else wanted to push him toward design. But so 2 have already found a job. 1 guy went to get an MBA, which is a different route, and we have 1 other student who is doing the graduate. I mean, she's working on her master's now. I guess we haven't had anyone who couldn't find a position. If that's what your concern is.
I mean, that was like the acquisition that nobody knows the school yet as an aerospace program.
Yeah, it takes a little bit of time, and that's just a normal process. You shouldn't really worry yourself about the accreditation.
I mean, I've talked to one of the professors I know that was in aerospace field and told me I wouldn't even let them tie my shoes. He used like phrase like that, like they haven't given any graduates, and
I didn't understand what you talked to someone who said what?
he said, I don't feel their work with them. I don't trust their capabilities yet.
Okay,
That's what
that
he said.
makes sense. Yeah. What did you expect? Is he here? He's in this school? Okay, that's their opinion. I mean, you are also welcome to transfer anytime you want. Yeah. I mean, I don't know how to answer that though. It's some random guy's opinion.
That concern that I had about graduating from aerospace from UofSC.
Is this person someone who is in the ME department?
No, it's he was working on aerospace field. That's right.
Well, he's in this school, but not in the ME department.
No, he's in engineering department.
At where?
He's in engineering department.
But he's not in mechanical engineering.
I don't know about it, but I know
And he has an opinion on the aerospace program.
he has an aerospace
Okay.
engineering thing in front of him.
Does he know anything about the aerospace program? What does he know?
I don't have. I know he's teaching aerospace class, one of the aerospace classes.
But he's not part of the mechanical engineering department.
He is, but he has like aerospace thing in front of his name.
I'm
tell
not.
you after class who it is.
Yeah, sure. Yeah. I mean that doesn't really matter.
Aero graduate school.
Yeah, but not like aerospace major. I know we have.
No, we
I feel like the graduate school is better accreditation than the major.
Oh, yeah.
So that's like a stepping stone to once we get our accreditation, they're gonna be like, oh, they've had a great aerospace master's program. Now
No, I kind of know who he's talking about. There are some politics going on inside the department. So, I mean, I have a guess.
I know Dr. Lyons is like us.
Yeah.
Like Alliance.
He hates us. On orientation, he's like, don't do it. It's an awful program. Yeah, we don't want it here.
Like Alliance said that?
Dr. Lyons looked through my schedule,
Yeah,
made my
yeah.
schedule.
Yeah, that was on orientation. He said, don't do biochem and don't do aero.
He's one of the guys who pushed for aerospace program. You know that?
I have a picture with
He told him not to do it.
schedule.
He told at orientation, he said that if you'd rather have an aerospace degree than have a job, then do it.
I think he pushed through because he wanted that money.
What's that?
He wanted the money for it.
I don't know. I mean, this is not that's not my position, right? To say what someone else's opinion is, if their opinion is true or not, or like what Dr. Lyons think. I mean, I don't know how to answer this.
Who cares what the professors think? Just think of like the employers. You're going to walk in there with an aerospace engineering degree. They're probably just going to look at that and say, you're hired. You're really. Okay, it depends on what you're doing. But aerospace doesn't just have to be aerospace. can do a lot of stuff with that.
Well,
Yeah, I mean, if you want to tell
places don't really care what's
That was a very interesting question, though. I didn't think someone would ask this in the middle of the class. But, okay, let's put a cap on it. And if you are, the accreditation part of it, if you're conservative, is just a bureaucratic thing that will happen. It will happen for the absolute worst programs. It will happen for the best programs. So that part doesn't give any legitimacy to any program, right? So that's not going to prove our program is good or not. So I guess it doesn't put your mind at ease, but that's how it is, as someone who has been involved with this for a long time. I mean, for a couple of years now. But whether the program is worth it or not, I don't know what to say.
I mean, I want to graduate.
I understand that. The thing is, if that's why I asked you if this guy is a part of the mechanical engineering department, because we are under the mechanical engineering. If they are part of this program, and if they are saying this program is not working good, they're just probably complaining for some reason, because they could have been involved, they could have made the program better from the get-go, right? So, I mean, you want to take it with a grain of salt. Doesn't mean the program is good, though. That should be your judgment. Okay? I guess my answer I don't know how to put you guys at ease with this new program. But our graduate could find a job. So I guess that's the only part that can prove something. What was it?
I said we'll all know the alumni network right when we get out of school. We are the alumni network.
I guess that's definitely it. Okay. So let's, and all of this is going to be on YouTube, so. That's it. I like that the lines. YouTube is up. I didn't say anything bad about it. Okay, so let's move on to the review of thermodynamics. And what time is it? 2:52. Okay. Let's move on to the review of thermodynamics, and then if we have extra time, we can come back to this interesting discussion. Okay. So my expectation for you guys is that you should know whatever we discuss in the first two or three lectures of the class. If you don't, that's all right. Just let me know, and we'll try to, I guess, expand your horizons and answer any questions you might have. Thermodynamics in general is a study of energy and how it's transferred. There are a couple of things we have to define before talking about the first law and the second law of thermodynamics. We want to define the closed systems, open systems, control volumes, and also the boundaries, the system boundaries in general. We also are going to move on to things that are going to help us describe these systems. The systems can be studied at a macroscopic level. Macroscopic. Or a microscopic level. Things like temperature, density, pressure, and all of things are of interest to, or volume, specific volume, whatever you want to call it, is of interest to us. One thing that I need to mention before moving forward, whenever I use this means that I'm talking about volume, and whenever I use just a simple V, I'm talking about the velocity. Both of these terms are very common in this course, so make sure not to confuse them. So a question for the class. Who can tell me what is the definition of a closed system? We said all work is done. Work is done within the system. Is this a strong enough definition? Do you have anyone else who wants to add anything to this?
There's no work coming in or going out of the system.
There is no work coming in. What does work coming in mean? Work is different from heat, isn't it? Okay, so either entering or escaping system. What else? What is the one specific characteristics of a closed system? That's the first law, though, right? I mean, can change, but then that's no matter. That is the biggest part of this closed system. There is no mass transfer. So the system boundaries, a closed system's boundaries, is closed to mass transfer. Work can be done on the system or done by the system on its surrounding, right? Heat can come into the system or go out of the system. Okay, we can heat the system up, or the system can heat up the surrounding. And just to make sure we are clear, system, surrounding. So surrounding refers to the environment around the system, right? Or we actually call it the environment as well. So there is no mass transfer between the system and the surrounding. That's the main property of the system. Okay? We also actually call the system a control mass, meaning that its mass is a control value. We have some control over the mass. We have absolute control over the mass of the system. And this is defined, this is actually in contradiction, it's direct contradiction. It has direct contradiction, or with open systems. Who can tell me what is the definition of an open system? Yes. We usually use control volume as synonymous with open systems, but they're not really synonymous. Open system generally refers to a system that, a system from which mass can transfer, can go out or come in. Which is true for the control volumes, but we have one additional constraint when it comes to control volume. Who can tell me what that is? What is the constraint we have in control volumes? So control mass was a system with a specific mass. There shouldn't be any mass change in the control. Yes? No, not necessarily. Volume of the control volume doesn't change. So control mass of it, this type of system doesn't change. Control volume, its volume remain constant. Its shape may change, right? The density inside of it may change because of the change in mass or whatever, right? But the volume does not change of the control. And we are going to use both of these in propulsion, but we are mainly focused on the concept of a control volume. Who can give me some examples of this control volume? A standard turbine, in general a jet engine, right? You have a specific volume, as long as it doesn't have any moving parts, it's a regular, just simple jet engine, its volume is going to remain constant, right? You have an inlet, outlet, you know where the inlet and outlet is. The parts, the frame of the jet engine, the case of that jet engine doesn't really expand, right? So its volume is going to remain constant. But we have mass transfer going in, air is coming in, fuel is coming in, and you have combustion. There are a lot of things that are happening there. The volume itself doesn't really change from a macro perspective. Another type of system that we have is called the isolated systems. Who can give me an idea of what isolated systems are? It's pretty self-explanatory, right? Systems are supposed to be isolated, which means that there is no mass transfer, there is no energy transfer, there is no nothing, right? It's just a system. You want to keep, you want it to keep its energy, you want it to keep its mass. Like an ideal, I would assume an ideal thermal bottle, like these thermos devices that you have, right? In an ideal world, you want it to have no amount of energy transfer with the outside, right? And as long as its door is closed, you want it to have no mass transfer, right? You don't want it to have any leakage, right? Any questions? Very simple concepts. I just want to make sure we cover everything. Okay. This is very. Is there anything new here? Control volume, control system. You have seen these many times. The next step for us is to talk about the extensive and intensive properties. Extensive and intensive properties. Who can tell me, or who? You haven't had to. Yeah. Who knows what are the extensive and intensive properties? Is this something that rings a bell? No, no. So extensive properties, in general, are defined as properties that do depend on the size of your system. And we can define intensive properties as properties that are independent of the size of your system. To get the ball rolling, I'm going to give you an example of both of extensive properties first, and then I'll ask you to come up with some examples of it. Think of some examples. So like properties that do depend on the size of your system, very simply you can say mass. Because mass does depend on the size of the system, right? If your control system or control volume, doesn't really matter, is bigger, and if there's nothing moving in it, it's just a stationary condition, if you're not heating it up or anything, as you make your control mass bigger, as you choose a bigger control mass or control volume, its mass is going to be higher and higher and higher, right? If you are not doing any work on it, if you are not heating it up or nothing. At a stationary condition, your mass is going to change. So your mass is going to be, mass in general, is going to be an extensive property. What are other extensive properties that come to your mind? Pressure. So, what else? Volume, right? Volume, as you increase the size, your volume changes, right? And but what can we say about pressure? Does pressure depend on the size of the system? Sometimes, no, yes. You have to elaborate. Whoever, I can't see whose lips are moving, so I don't know who is answering this. I just know the general area. So you have to either elaborate on your answers or raise your hand, as Karim did. Yeah, so who wanted to go first? If you have, yeah, sure.
So, like, pressure could change depending on the size of the system, because if you have like a fixed volume of that pressure, of that gas or anything in water, if you expand it, the pressure would decrease and things like that.
That's a good point, and that is true. But here we are not talking about expanding the system, right? Just choosing it. Like when you're choosing a control volume, here I can choose a control here. This can be my control volume, or this can be my control volume. I'm not expanding it. I'm just choosing a different frame, right? That expansion itself is doing work, right? You don't want to do anything. Just as long as it changes its size without any work, or essentially you're choosing a different frame. Any other one who wanted you?
I was going to say, because, like, for example, in the fluid mechanics, the pressure doesn't change depending on the size of the system that we have on the fluid that's flowing through. That's why I said that.
Okay. Pressure. Okay. Yeah, pressure. What do you want to add something?
I was going to say, yes.
Who is talking now?
I'm talking.
Okay.
I was going to say yes. To look at the gas and say everything equal to any pressure, and everything else except volume stays constant, then the pressure would be this side of the system.
You are making the same mistake. What is your name again? Patrick did. We are not doing any work on it. We are not changing the volume. We're just choosing a different frame. Like that's it. So you are moving your focus from this frame and applying it to this bigger frame here, right? Nick, do you want to add something? Yeah, then you and Karim are true, and I gave a couple of yes.
Yeah, I'd like to retract the pressure. I thought the same thing. I thought we were changing the size of the system, not the
Okay. So pressure does not depend on the size. Pressure is essentially force per unit area. And in this room, force per unit area here in this frame is going to be the same as force per unit area at the same location, just in a bigger frame, right? Pressure is not going to change. But the volume of the frame is definitely changing, right? The same is true for temperature and also density. So both these are not extensive properties, right? And we usually don't treat them as intensive properties as well, because intensive properties are defined as extensive properties that are independent of your size, right? And we will talk about those a little bit later. Well, volume. And the other property that actually does depend on your size is the energy. Internal energy of the system, and we use in general energy is an extensive property. So there are some cases that we want these properties to be independent of the size, right? You just divide them by your mass, essentially, to get to make sure they are independent of how much stuff is inside your frame. right? If you divide your mass by mass, it's going to give you 1. Your volume is going to be V divided by mass, and your energy is going to be also U divided by mass. Enthalpy is also another extensive property, and for the intensive property part of it, we just divide H by M. Any question here? So moving on to the next thing that we want to. So you didn't talk about extensive and intensive properties in your thermal. Equilibrium. Let's talk about equilibrium. Thermal equilibrium or thermodynamic equilibrium. What is this thermal equilibrium?
Forces acting on either side neutralize each other.
Forces acting on either side.
So like the pressure outside the system and inside the system would be equalized.
Okay. So essentially what you're saying is that the work done on the system or the heat transfer to the system should be 0. Is that what you're saying?
Mm-hmm.
Okay. Do we have any other opinion on this?
Q net equals Q plus
You are
It has
essentially
to be the heat, like,
You say like the rate of energy changes there.
rate of energy change is 0. Okay. Energy change of the whole system. So essentially what you're saying is that whatever heat we are putting into the system should be equal to the amount of work done on the system or done by the system, right? Okay. So equilibrium condition, all of you are kind of true, right? But not exactly. Equilibrium condition usually refers to a state inside your system or inside control volume at which all of these properties are going to stay the same, be the same all over the system. Right? Your temperature at one part of the system is going to be like 300 Kelvin, and at the other part of the system it should be also 300 Kelvin. Well, how can we have work, or how can we heat up the system and maintain this, right? Because it will take some time for heat, for example, to penetrate into the system, right? Some part of the system will be hotter, other parts will be colder. That essentially can be done as long as you do your heating slow enough. To give an example, if you have a piston, if you are moving this piston at a very slow rate, you are doing work on the surroundings, right? Work is being done by the system, right? Work is not 0. But as long as it is happening slow enough, right, that essentially keeps the temperature at every time. At the next time, the temperature is going to be different, but at every time, temperature all over the system is the same, right? If you move this slowly, then you can say you are in thermal equilibrium. So thermal equilibrium doesn't really mean a steady state condition. Doesn't mean changes over time is 0. Essentially means that changes over location inside the system is 0. Okay? So there may be some energy transfer over time. As long as it's being done slowly, it should be fine, right? I'm pretty sure you are aware of the different measurement systems we have. We have the metric measurement system, SSI, and we also have the imperial system or the British system. And we are going to use both of those systems in this class. I was trained in metric system, and in graduate school we don't really use British system, so I'm more, I guess, familiar. I'm more comfortable because there's nothing to be familiar with. I'm more comfortable with the metric system, so most of my examples are going to be in metric system. If this is something that you can't really comprehend, just let me know. I'll try to change my examples to the imperial system. But I don't think we need to go over the differences. I'm pretty sure at this point in your career and education, you already know. No. If you, it may happen, but it won't be the focus of a problem, right? So if you usually, let me put it this way: if you needed to convert something to another thing in an exam, you can ask me. I will give you the conversion rate. Okay? Because that the conversion of this from metric to British system is not going to be the focus of the class. I mean, the idea is you already know how to convert, and if you don't know, that's your problem to figure out. Okay. Okay. Let's talk about the first law of thermodynamics. Who can tell me what the first law is? And this will be, you will get a bonus point if you give me the correct definition of the first law. Yes. What was your name again? Drew. Okay. Energy cannot be created and destroyed. Exactly. The energy, thank you, cannot be created and nor destroyed, right? Which essentially means that energy is conserved. The conservation of energy. In terms of mathematics of it, we are going to represent the first law by this. The changes of internal energy of a system is going to be heat transferred to the system minus work done on the system. Right? And just have to keep in mind that the work, this is just a sign convention. The work is going to be positive if it's done on the system. And the work can be negative if it's done by the system. The same can be true for heat. If it's heat transferred to the system, heat is going to be positive, and if heat from the system, it is going to be negative. If you wanted to use a different sign convention, that's alright, I don't really care, as long as you are consistent. But if we want to change the work sign convention, for example, let me actually pose this as a question. What would happen to the first law if I change the sign convention for work? Which essentially means that what will happen to the first law if I say the work done by the system is positive. No. That's just a convention. Doesn't really change the physics of it. Can you repeat what you said? I guess, but my question is, what's going to happen to the equations? It is just a sign convention because there is no negative work, right? That doesn't really mean anything. It's just the direction of the work that we are assigning. That this is a negative direction, this is a positive direction, right? I'm just changing my perspective. That's it. I'm just treating a work that was considered positive as negative now. What is going to happen to the main equation? Yes. That's it. So if you change the sign convention, you have to make sure that this change in the sign convention is consistent throughout that doesn't really violate any laws. It's just a mathematical game we are playing with this, right? It's just a convention. Any questions so far? Okay, so how can we calculate the work done by the system? What is the main equation? Work is the integral of force FDS, essentially. Essentially, the amount of movement you have created, right, by applying some force on something. That's your work. How can we calculate heat? That is a little more complicated. You have to take a heat transfer class to be able to calculate the total heat, but we usually have like simpler equations that we'll get to when we want to talk about it. But the force in general, this is the main equation that we are going to put between two specific points in the system. Is there any way for me to transform this to an equation that is based on pressure, not based on force? Because we usually work with pressure, we don't really work with force, right? Think about it. What is the relationship between force and pressure? One of you. Yeah.
Pressure is force per area.
Force per area, right? So essentially we can say force is pressure, this is pressure, multiplied by area, right? I'm going to substitute force with this inside this equation. So W is going to be equal to, from S1 to S2, P A ds. And we said this ds is a change in location. So if you are dealing with a piston that is expanding, at the initial condition your S1 is here, then it will, at the second time it will move to S2, right? This ds is this, right? Delta S. I mean, in this case, this is going to be delta S, right? So, how can I change this equation a little further to make it look more like a thermodynamic equation? In thermodynamics, we usually deal with equation of states, like ideal gas law, PV equals to nRT, right? Or P equals to rho RT, whatever. So we usually deal with volume, density, temperature, pressure, right? We don't really deal with the area or the distance traveled. So how can I change this to be a little more thermodynamics friendly? It's not that hard. I just bring this into this derivative. ADS is essentially going to be equal to the derivative of volume. That's area, this changes in volume, right? This amount of change in volume. Yes? Does this make sense? Or do you need more explanation? No? Yeah. You have a question? No. So, work is going to be equal to integral of P dV in general, right? And we already have the ideal gas now. We actually can take a look at the instant, I guess, energy change, if you will. Meaning that we are not looking at the equation at 2 times. We are just looking at this equation at an instant, at one time, and everything will transform to the derivative of your internal energy change, for example. So if you're looking at an instant, your delta E is going to be transformed to derivative of internal energy, and your Q minus W is going to be a very small changes in Q, or delta Q minus delta W, very small changes in W, or the rate of change in, and we can bring the T, let me actually rewrite this, or we can say the changes of E with respect to time is Q dot minus W dot. Any questions so far? So let's have a very quick quiz in the first lecture, and we'll move on from there. just to make sure all of you have followed the class material. And actually, the quiz is also on the. Did anyone see the lecture posted online before the class? No? Okay. If you had seen it, then it would have been much easier for you to, I guess, answer this quiz. This is the quiz. We have a 0.4 kilogram of a certain gas that is contained within a piston cylinder assembly. The gas undergoes a process for which the pressure-volume relationship is PV to the power 1.5, and volume here is the only thing that is going to the power 1.5 is constant. The initial pressure is 3 bar, the initial volume is 0.1 meters cubed, and the final volume is 0.2 meters cubed. The change in a specific internal energy of the gas in the process is, we have the internal energy change, that's negative 55 kilojoules per kilogram. There are no significant changes in the kinetic or potential energy. And we want to determine the net heat transfer rate for the process in kilojoules. Okay. How should we solve this problem? Please just, is there anyone who doesn't have a piece of paper? I mean, I don't have any extra, so please borrow from your friends. Do you have any questions about the problem itself? Is this clear? Okay. Is there anyone who can give us a clue on how to solve this problem? Yes. No. Okay, but where would you start though? You will start with W. Pressure and volume. Yeah, okay. You want to add something? Pressure at 0.2, exactly. So you want to start by, you want to, in general you want to do what Lawson said, but you want to start by finding the pressure at 0.2, right? Because we have the final volume at 0.2, right? And the equation PV to the power 1.1 is constant, which essentially means that P1V1 to the power 1.5 is equal to P2V2 to the power 1.5, right? You have P1, you have V1, you have V2. You should be able to find P2. Let me actually write it down. Let me write it down here. P1 V1 to the power 1.5 is P2 V2 to the power 1.5. You want me to go back to the... Okay, let's. Is there anyone who has solved? I mean, you don't have enough time to do it, but is there anyone who has solved this already? Okay. I'm gonna give you 1 more minute, and if you could solve it, you'll get a bonus point, of course. Okay, let's wait here. Let's actually. You are the only one who solved this. Anyone else? Okay, I believe you, and I will give you the bonus point. So let's solve this, because I want to make sure we all have the solution. We all understand the solution before finishing today's lecture. So the first is that the goal here is essentially to find the Q, right? We already have the U as an intensive property, right, divided by the Lagrange, right? So we want to transform that to the extensive property part of it as well, right? So we have delta E, or in this case, what's going on? Delta U, because the other parts of internal energy were 0, right? The potential energy, all of those parts are 0. So delta U is equals to delta E, which is equals to Q minus W, right? But we have the small u's, right? We have U2, a small u, which is the intensive property, minus U1. We just have to make sure we multiply it by an M to get the capital delta U, right? The delta U capital, which is going to be negative 55 multiplied by 0.4, whatever that value is. And let's see what else. Yeah. And then we need to go to W to be able to find W. We want to take the integral of PdV between states 1 and 2, but we already know that PV to the power 1.5 is constant, right? I'm just going to use a C instead of constant, and then I'm going to write everything as a function of P, right? So it's going to be C divided by volume multiplied by to the power 1.5. So your W is going to be equal to integral from 1 to 2 C divided by V to the power 1.5 dV. C is a constant, it will come out of the integral. And this part was the hard part of this problem, actually. dV divided by V to the power 1.5. What is the solution to this integral? This is a very simple integral. V to the power negative 1.5 dV. Just have to add 1 to the power. It is the solution of your integral. So it's going to be C divided by let me actually C V2 to the negative 5 minus V1 to the negative 5, right? Is there anything else I need to add to this integral? We also need to add a negative 0.5, because when you take the derivative, the power will be multiplied by the integral. If you don't really remember this, I'm pretty sure you have learned this, just go back to your mathematics or come to my office. We'll go further in detail about how to take this integral, right? And well, from this equation, we also know that PV is equal to this constant. So you just plug that in for C, and your W is going to be equal to P2 V2 minus P1 V1. And I'm sorry, what happened here? And all of this multiplied by 1 divided by -5 or -2. We have P2, we have V1, V2, we have P1, we have V actually this is also V1. We have everything, we have already calculated all of this. Should be able to find W. The W is calculated. The same is true for delta U. We should be able to calculate Q. Is this clear? Okay, so that's it for today. Let me stop the recording.